All right, hello everybody. Let people wrap up some pictures here. Thank you again to everybody for coming today to Purdue University for our portion of the NSF DOE Vera C Rubin Observatory First Light Watch Party. And we are really excited. It was really great to get to watch that presentation from Rubin and get to see those images for the first time. I'm Dylan Caudill. I'm a first-year graduate student here at Purdue,
And I'm Danielle Dickinson. I'm a fifth-year graduate student. We work on supernova science, and we're super excited to hear some experts later talk about the incredible science, about supernovae and other realms of astrophysics that Rubin will enable. We are going to hop right in with a video from a Purdue professor, John Peterson.
Hi, I'm John Peterson. You've just seen some of the new images of the Rubin Observatory. Now I'll talk a little bit about the capabilities of Rubin and tell you a little bit about the involvement at Purdue. I first worked on Rubin over 20 years ago. I built the simulator that Rubin used in the R&D and construction period and received 6 contracts over the years to do various tasks. If you look at the 2 images in this slide, you'll see the Rubin Observatory last year on the left, and on the right is an artist's impression of Rubin drawn with a simulation of the stars and galaxies in the background that I did many years ago. So this kind of showed the long journey going from a concept on a piece of paper to the actual Rubin Observatory. Here's some key properties of Rubin. Rubin's an optical and near-infrared telescope. It goes from the U-band all the way to the Y-band. It's located in Cerro Pachon, Chile. It surveys essentially the entire southern sky every few nights, up to 24th magnitude. And it achieves a deep survey over 10 years, getting all the way to 27th magnitude. Rubin has a unique 3-mirror design with 3 lenses and a filter. It has a giant 8.4 meter primary mirror with a tertiary mirror built into it for an effective size of 6.7 meters. It also features the largest astronomical camera ever made, a 3 gigapixel camera that has 189 individual CCDs. Those CCDs will take a series of short exposures of 15 seconds. Probably the most important single key feature of the Rubin Observatory is its large field of view. It has a unique field of view that's over 10 square degrees. That's several times bigger than the full moon. This is achieved by its unique 3-mirror fast optical design. It's f1.1 design. This allows overall a short focal length, which makes the camera to be as small as possible, even though it turns out it's the largest astronomical camera ever made. If you want to do a big survey, the most important quantity is something called étendue. Étendue is the product of the telescope's aperture times the field of view. You can see by the table to the right a series of other past survey telescopes that were designed to do a large survey, and their étendue compared to the Rubin Observatory. So in almost all cases, Rubin exceeds other telescopes by about an order of magnitude. Étendue then tells how much light you collect from a survey per time. So it tells you how fast you can survey the sky and collect as much light as possible from all the stars and galaxies. So if you think about it, Rubin can do a survey in 1 year that other observatories would have taken 10 years. So over its 10 years, it will do something 10 times larger than many other surveys. One consequence of that large étendue is that it has a very large data rate. So if you think about it, every 15 seconds, a 3 gigapixel camera will generate essentially tens of terabytes of data per night. To put that in perspective, even if you were to sit down and look at a TV screen all day long, and you looked at a 4K image every second, you'd actually be about 25 times too slow in keeping up with the data rates of Rubin. So that just highlights how you have to automate all the processing, and no one really will be able to ever look at all the data individually. Another consequence of this fast survey is that there's really no point to individual proposals anymore, since you can survey the whole sky every few nights. So that also means that the data will become public to the community after it's taken, and people can do their individual science on whatever part of the data that they're interested in. Let me tell you a little bit about the Purdue involvement in the Rubin Observatory. There was some work done in developing the corner raft, which includes the guiders and wavefront sensors. And my group also built the simulator, which was used both in the R&D and the construction period of the project. This used a novel method simulating photons using a Monte Carlo approach, where you individually take photons from stars and galaxies, and then model all interactions in the physics of the atmosphere, the telescope, and the sensor as the photon propagates through the system. This idea originally was thought to be impossible due to the high photon rates. If you think about how many photons come in from an optical telescope, especially one that's the highest Etan-2 telescope, it's quite daunting. But Monte Carlos can be quite efficient. A number of novel computational techniques we invented allowed it to be pretty fast to generate images, at least to study where the possible problems could come from. This is increasingly more important with larger surveys because with more data, more objects, you can make more detailed measurements. Inevitably, there's going to be more and more systematics that come with making those measurements, so you have to understand more of the details probably than we ever understood before. So this approach proved very useful in the early stages of the project to pass the critical reviews to get the project approved, as well as to verify and do various studies on the design and various concepts as the project was started. Here's a movie of the photons from using the photon simulator code called PHOSIM. Here we start from a set of photons from stars and galaxies across the universe. And as you can see, they come across the universe, they propagate through the layers of turbulence in the atmosphere, then they hit the primary mirror. You saw before that the mirror being adjusted by the actuators. And then they go into the lenses of the camera, only get through the blue filter, and then finally you see the photons ejecting photoelectrons in the silicon of the sensor. This simulation was done just to simulate a single star and a single galaxy. But it can do this whole simulation in less than a millisecond. You can also see some of the physics behind this. You can see the atmospheric turbulence, the way we model it with a series of turbulent layers that are drifting across the Rubin telescope. This has the consequence of blurring the images. You can see in the other movie an image of a star and the famous speckle pattern. This also causes the positions of stars to shift slightly and the ellipticity of objects to get slightly distorted across the field. It kind of correlates with the wind direction. Another important thing is the surface deformation on the mirrors. In this movie, you see the mirror shape of both the primary and tertiary mirror being corrected by the actuator system. This causes a number of effects that kind of blurs the images and causes astigmatism due to both thermal gradients across the mirror, as well as the gravitational sag of the mirror itself from the support system. Another important part is the details of exactly how the sensors work. So in this simulation, you can see the electric field lines generated by a slab of silicon. The electrons have to make it to the pixels. And if these field lines aren't perfectly parallel, they end up in slightly different pixels than you might expect them to be in. This causes various distortions of the image as well as causing the usual charge diffusion in the detector. There are so many different pieces of physics in these kinds of simulations. You can see a huge list of them in the green box on the right. And the challenge is to match those up with individual distortions or various systematics that you can see in images. And you can just see the complexity of the two. Here you can see how the individual physics connects to various image properties. We've also extended this code to simulate lots of other telescopes after starting with the Rubin Observatory. You can see both professional astronomy telescopes as well as amateur telescopes and even the human eye. So here's that original image you saw on the first slide, simulated image of what we thought we would see with Rubin with various stars and galaxies in the background. You can see a bright saturated star in the upper left and many other stars and galaxies throughout the image. every single photon in this image has been ray traced through the full set of physics described on the previous slides. Here you can see an appreciation of even how big the 10 square degrees is, and even in a 15-second exposure, how many stars and galaxies you're truly collecting. So this is a full simulation. All the stars and galaxies and even the background has been simulated through the photon simulator. It totals about 20 trillion photons. And as you zoom in, you can appreciate just how much data there is on the individual chips, as well as zooming in all the way to see the individual stars and galaxies. Survey begins very soon. The data preview will be available to everyone at the end of the month. This covers an initial set of images. You'll talk more in the Q&A about individual science people are interested in at Purdue, but nearly any topic in astronomy is covered by the Rubin Observatory. So this includes finding all the near-Earth asteroids, making a 3D map of millions and millions of galaxies, mapping the edges of the Milky Way and as it's still forming today, finding about 1 million supernovae every year, and along with that, probably finding dozens of rare, interesting new objects we don't even know about, as well as answering some big questions and making precision measurements about dark matter and dark energy. Just about any astronomy topic can be covered by this comprehensive survey. It's an exciting time for Purdue physics and astronomy. We can all look forward to the images Rubin produces over the coming months.
So thank you, Professor Peterson, for that amazing video. It was really cool to get to see those simulations and have him talk about his work a little bit. I'm going to talk to you very briefly about some of the other efforts that we have at Purdue that you may not think of immediately as we go along. So right above my head, there's a couple of pictures of students standing in front of posters. These students are from the Data Mine. The Data Mine is a course that you can take, and basically it gives students the chance to interact with big data and try to answer those questions across physics and astronomy. These were actually both of the groups that I TA'd for, and they were working with data from another survey telescope called ZTF. And a lot of the work that the Data Mine in astronomy is focused on is preparing for Rubin. So once that data becomes available, that class will shift and change into trying to answer the new questions that we get from Rubin. Up in the top right, there's a little SMAP sticker. That is for Saturday morning astrophysics at Purdue. It's one of our biggest outreach programs within the department, and it's done once a month every Saturday. It's a fantastic thing. Well, as it was discussed in the Rubin live stream and a little bit here, this data is going to be publicly accessible, and there's going to be a large amount of citizen science that they are going to ask people to do, and that's where programs like SMAP can chip in and outreach can become very important. And these all contribute to the research ecosystem that is provided by Rubin data alone, and it's going to be very exciting for Purdue.
Yeah, and the tremendous amount of science, particularly for supernovae for our research group under Dan Milosavljevic, knowing more about supernovae as a population will tell us more about the intricate physics so we can study other objects, and Dan will talk about the supernova remnants. We do really great work with up-close and personal analyses of particular supernova remnants, and Rubin will tell us more about supernova physics, which will kind of cause this positive feedback loop in understanding these objects as a whole. The really incredible thing about Rubin is that it's a completely public survey. The data stream is completely public. Everybody in this room will be able to access the data and use science from it. And Rubin will be an incredible discovery machine. It will find millions of supernovae per year, and those supernovae will need to be followed up with to determine critical physics that power their light curves. And this is where we come in as professional astronomers, and also citizen scientists will help us as well too. Here I've highlighted one such astronomer that we work with quite frequently. He is very talented and takes a lot of data, chucks them in is great, and there's a lot of citizen scientists out there. For example, there's a light curve of an object that exploded a few years ago, supernova 2023 IXF. The red, yellow, green, and blue points, those were all contributions by citizen scientists. We would not have a light curve like this without them. And now we're going to turn things over to two panelists and a Q&A section. So we will invite up Dan Milosavljevic and Braden Gerritsen to the stage. The other two folks up here, Professor John Peterson and Dr. John Banovitz, they are joining us on Zoom, so they will pop in a little bit. Professor Dan Milosavljevic is a professor at Purdue here in the Department of Physics and Astronomy, and Braden Gerritsen is an extremely talented researcher that just graduated here.
It's my turn to talk? Okay. Hi, everyone. It's really exciting to see this turnout on a summer day at 11 and now noon. I just saw an article with a headline that I completely agree with. Second to the launch and successful debut of the first images from the James Webb Space Telescope, we've now seen a transformational facility just at the beginning, stretching its wings, as it were, on the cusp of potential. So yes, what do I want to discuss about? So our own science, I didn't get a lot of highlight in the presentation you just saw, I think largely because the kind of work that will be done regarding stellar explosions, supernovae, will take more time. We need more monitoring over a longer time scale. This is kind of low-hanging fruit where they had certain areas of the sky they could monitor and look very deeply. So what is the science that I do? Basically, stars much larger than the sun, and stars that, like the sun, that have a nearby companion to add some material. At the end of their lives, they undergo a tremendous process, okay, with a lot of energy. And this energy is needed to produce the raw materials for new stars and planets and that make life possible for us. So by understanding supernovae, we're understanding our cosmic origins. A lot of the work that I do using space telescope like James Webb and the Hubble Space Telescope does targeted investigations of individual objects. And there's a lot of value in that because you can see where all the stuff is. You can make careful measurements of the velocities of the gas and the types of gas that are there. Compare that to simulations. But as much as I go on about a gorgeous image like this, supernova remnant Cassiopeia A, that's the debris field of a star that exploded about 350 years with respect to when the light first arrived here. As beautiful as that is, as science-rich, it's only one example. Okay? And there's only a couple dozen examples like this that we can do this kind of in-depth analysis. And the diversity of kind of stellar explosions that they are, the range of the masses of the stars, the range of how far away they may be, how big they may be, okay? The timescales of how they share material. All of that gives a range of stellar outcomes. So we really need a larger sample pool, not hundreds of events, but we need hundreds of thousands or millions of events, and that's what Rubin Observatory is going to provide. I'm highlighting here a project here at Purdue we've been running for several years. I see Mark Linvell and others in the audience that are participants in this. We've been trying to prepare for the massive data flow from Rubin. So you saw in the presentation the enormous image, right, from one field of view. And they will use this massive camera to constantly survey the visible sky again and again and again. Remember, any human could not physically look at these images and examine it. It needs to be processed by computers. But even then, we're going to get, on average, 10 million alerts about sources, stuff in the sky that's changing. And even that, even with all of the large astronomical network that we have, it's too large for us to pursue every object. We need help. We need an automated system that guides us to the most science-rich objects. Okay? So our project, the Recommender Engine for Intelligent Transient Tracking, REFIT, in short, is that thing. Think of it as like a recommendation engine, much like Netflix, okay? Each of you, you may have different profiles. I share with my wife, and when I log on, I get a very different set of movies that I'm interested in than my wife. Okay? And I won't go into details about that, but I'll leave that for you to decide. So, while some astronomers may be interested in cosmological applications of supernova explosions, so measuring distance of galaxies and trying to get a sense of dark energy, our team is interested in the explosion physics. So the types of supernova explosions that we're interested in can be fed to us through a recommendation engine like this. And even on broader terms, the professional network is not large enough. There aren't enough telescopes professionally run to be able to pursue the plethora of explosions. Any given night, there'll be about 3,000 new supernovae, in addition to tens of thousands of supernovae any given time we could be pursuing. So the idea is to crowdsource the help of citizen scientists. So these are volunteer astronomers with their own amateur equipment that can be guided to these science-rich targets and relieve the professional astronomers to pursue perhaps the fainter objects. So I think Braden's going to actually go into a little bit more detail about that.
Yeah, so a lot of what my work has been focused on, and I've been working with Dan for about 4.5 years now. I actually got started in the class that Dylan mentioned earlier. In some cases, when you're discovering millions of supernovae, you're looking for the 1 in a million object that you're really not going to find with any other telescope. So how do you actually find that in real time, actually get good data on it besides just what the survey collects? So Rubin's going to, provide us with hundreds of thousands of supernovae per year, and then there's actually a lot of machine learning and modeling work that goes into to be able to automatically recommend these objects to astronomers around the world. And we're basically doing weather forecasting, but for supernovae, trying to understand how they're going to evolve, and then trying to understand which ones are best for different science cases. And then once we have this, we actually will distribute it out to astronomers and amateurs so that we can go follow it up. And like Dan was saying, there's many, many different kinds of science cases that you may want to pursue, and there's on order professionally, 10 or 20 telescopes that are actually really suited to follow up objects automatically in the kind of way that Rubin needs. And if you're interested in cosmology, there's going to be like 70% of the supernovae it finds, will be 1As that are fantastic for cosmology. But for other fields like mass loss or peculiar supernovae, over the course of a year, only maybe 1% of the data, or even less than that in some cases, will actually be what you're looking for. So our job is trying to point astronomers in the direction of the data that they actually want.
Okay, thank you guys so much for speaking a little bit about just the impact of Rubin at Purdue. We're going to open things up to a Q&A, and I first wanted to start out actually by asking Dr. John Banovitz some questions, if we could.
Is John here? John, you out there?
You guys.
It's great to hear your voice, John. He is a Purdue alum who completed his PhD here under Professor Dan Milosavljevic. John, do you want to tell us a little bit about yourself and how you came to work with Rubin?
Yeah, so I was at Purdue from 2016 to 2022 as a grad student working with Professor Dan Milosavljevic. That's actually how I first learned about Rubin and LSST, was helping out with the refit project and doing our own follow-up on some of the supernovae. I then transitioned into a postdoc at Brookhaven National Lab, where I worked with the LSST commissioning team, focusing on the camera, as well as data verification and validation. And through these projects, I was extremely fortunate enough to go to Slack multiple times to go into the clean room and work with the camera kind of more directly, as well as spend many months in Chile at the observatory, working on the camera and working on getting the camera ready to go on sky. And so it was a great joy and also a little bit of a relief to see those images and how beautiful that they turned out.
Sorry about that. We also notice you're in Chile right now, like at the front lines.
Sorry, I just got back. I'm
Oh, okay.
transitioned to a new postdoc. I'm now at Lawrence Berkeley National Lab working with a different survey, the DESI survey.
Ah, wonderful, fantastic. We were actually wondering if you could speak on a little bit of the commissioning process and kind of what the past few months have been getting ready for these images today.
Yeah, the commissioning process is very fun, very exciting, a little hectic. As you're at the observatory, there's many things that you need to work on in order to produce these images. So for example, we would be working with the cooling team. We need these CCDs down to minus 100 degrees C, and we actually need one of our components needs to be cooled down to minus 100 degrees C. And so we are working a lot with our Chilean coworkers to get these cryogenic systems set up. You have to work with the people who are knowledgeable of the mirror system and I believe the adaptive optic system, so that all of your images are in focus. We also had a little bit of lab work. You have to work with the data management team. As Professor Peterson said in his video, you have a lot of data that needs to be processed, so much so that a human can't do it. And so as part of more of the camera team and the data verification team, I was looking, while a human shouldn't do it, we did have people look at it, including myself, to try and make sure that everything was all right, just at the beginning stages. And so there's lots of people. There were probably like 100 to 200 people down in Chile just working on getting the observatory and the telescope up and running. But that's not to include the hundreds to thousands of people around the world working on it, working with the data and the pipelines to make sure that our images are of the best quality.
John, it's so exciting to see you there now. Speaking about transients, I see some facial hair, so there's been some growth in the last 3 years since I saw you. I've gotten some updates along the way, and we'll have to carry this offline, but can you maybe speak about some of the biggest responsibilities? Everything from, for instance, at one point you mentioned the concern about artificial satellites. So Starlink, coming in the field of view and being able to avoid those and removing them.
Yeah, so on my side, it was primarily working with the sensors themselves and making sure that everything was working correctly. There were a few sensors that had like weird anomalies. How are we going to deal with them? Can we change things with the hardware themselves, or do we kind of have to change things in post-processing in order to make sure, again, that the data was of the highest quality? As for artificial satellites, there is a large team, I believe, at UC Davis and the University of Washington that are working with that. So they have their own pipeline of how to deal with all the satellites, because with Rubin's huge field of view, it's, I think, 1 in every 3 of the images will have a satellite in it. So you need a dedicated pipeline and a dedicated team in order to remove those satellites from the images.
John, you don't have to answer this, but Subspace Chatter has it that not all the CCDs are working 100%. Can you speak on what's still going on during commissioning?
There's some, at the beginning of commissioning, there were some CCDs that needed a little extra finagling to work. We've since got them working. There's still a little bit of ongoing work with a few of them, but yeah, I mean, they were the beautiful thing with Rubin is we have so many CCDs that even losing a handful is like a small percentage of the entire focal plane when you have 189 of them.
Right, right, beautiful. So there was, yeah, at the first images discussed in June, there was some, it seems like you've made improvements since then, and you have plenty of time to continue that.
Yeah, there's a lot of work done, not with me, but other people on the camera team and people at UC Davis that are working on getting those CCDs working, and they need a little bit of extra care and special attention just for them. And they're
Cool.
getting
Okay.
that right now.
Cool. Okay, I was nerding out there. I was just curious about the state of the instrument right now.
Yeah, perfect. Thank you very much. We're going to roll over to Professor John Peterson. Are you with us?
Yeah, hi, I'm here.
Perfect. Really quick, Professor, I just wanted to ask you, after about 2 decades of working on this, what's it like to actually get to today and see the real images compared to the simulations that you showed us earlier?
Yeah, it's pretty exciting. Yeah, like if you saw in the video I showed, the video where it was just a concept, it was just, an idea about what we are gonna do. To yeah, just seeing the images and the scale. Yeah, it's pretty exciting.
Yeah, and I wanted to follow up with that, or follow up on that with where do you go from here? What does your work look like now? Are you transitioning to other things, or are you going to continue to work with Rubin data?
Yeah, so I guess in two ways. One, since my group wrote the simulator, we're very excited to get some data at the end of the month and kind of check various things and explore some really, really detailed things about how the instrument works and that kind of thing. But I also have a whole uh, science program too. I normally, over the years, have studied clusters of galaxies. Um, so you saw one of those in their press event of even a piece of the Virgo cluster. Um, but Rubin, of course, will find and measure tens of thousands of clusters of galaxies much better than any other telescope and have these very deep images of them. Um, and personally, I'm very excited to work on something called weak gravitational lensing, where you look at some of the galaxies behind a cluster galaxy, look at their shapes in detail, and then use that to make a map of the dark matter in that cluster galaxy. And essentially, Rubin can start to do that over a big, big portion of the sky. So you can start to learn about how structures are formed in the universe.
Yeah, thank you very much. It was very impressive to see the simulations. I'd never seen those before, and thank you very much for that answer.
Our next question is for Dan, actually. And we were wondering if you could tell us a little bit about the differences in working with, say, JWST data versus Rubin data.
Great question. So I started a bit of that explanation in my slides. Powerful telescopes, very large apertures, so the size of the mirrors, they typically zero in on a relatively small portion of the sky. Rubin has a large aperture, but it's been designed to still have a wide field of view. And instead of zeroing in a small portion of the sky, it's going to have a very big field of view. On top of that, it's going to regularly patrol the sky. So whereas with James Webb, we had every year opportunity to pitch proposals and go through the whole peer review process, and we got the proposal approved, and then I got one snapshot of what CAS-A looks like there and then. This is going to be continually monitoring. It returns to the same patch of sky every 3 to 4 nights as it rotates through 6 different filters. That's where you get the color of the image. I'm actually interested in what filters were used to make those composite images. So with Rubin, you have this opportunity for wide field observing in chromatic. So you get panchromatic observations routinely. So this gives us an opportunity to patrol for many supernovae. I'll phrase it a bit differently. In the universe, a supernova goes off about once every second. Okay? And that works out approximately to one supernova per galaxy per 50 or 100 years. So instead of patrolling one galaxy again and again regularly, we patrol as many galaxies as possible to capture as many supernovae as we can. Rubin is where you want to be as far as parameter space for trying to capture supernovae, observing as much of the sky as possible and as many filters as possible. And just real quick, why do I need many filters as opposed to just one? Each filter is sensitive to a different region of wavelength, and if I have knowledge about what energy, what wavelength that photon is, I can compare them, the different filters, to give a sense of how hot the supernova explosion is, what gases are emitting, and how fast that they're moving. So while as gorgeous as James Webb and Hubble Space Telescope are, they have specific wavelength regions and they study only small areas of the sky. Rubin is needed to get a population scale assessment of the supernova population.
Thank you so much.
We'll keep going down the line to Braden here. So tell us what it's like being a young scientist. This is coming online right now. You're going to be able to work with this data for the rest of for the foreseeable future in your career, and you've already worked on it for an extensive amount of time, like you said, the last 4.5 years. What is it like to have these first light images, and how do you feel going forward with the upcoming survey?
I mean, it's pretty cool because when I started working, Rubin was supposed to launch like in a year from then, and then it didn't. But you know, the amount of data is pretty ridiculous. I mean, it'll be, you know, it's kind of like a data set that'll basically be studied forever, probably, you know, for the rest of our lives. It's not something that's easily to be topped. Just the, you know, the amount of supernovae. You know, if you were trying to look through all of them, you'd never probably cycle back on the same one twice. So the actual ability to, you know, do statistically significant like studies of these objects is pretty ridiculous. And then it really changes how other telescopes operate because it really informs where you point other telescopes like Webb or the other you know, large optical facilities that have a very small field of view. You can really target unique objects that you're really interested in rather than trying to observe large parts of the sky anymore.
Can I chime in working off of that? So how do I feel? I always get asked that question. So today I had an opportunity just briefly to compare what the newly released Rubin observation is of the Virgo cluster to, I would say, a state-of-the-art existing survey telescope, the DESI Legacy survey. And just blinking between the two, you see, I mean, the difference in aperture size, so the size of the telescope, resolution and sensitivity. And I'm already, my mind is blown at the change in the amount of data that's coming down. And we've currently, for the last 5 years, REFIT has been operating on a different survey called the Zwicky Transient Facility. This is what Braden's work has been largely been practicing for upcoming Rubin, which is just about online. And it's already been a challenge to be able to ingest that data set, which is at the order of, tens of thousands per year, supernovae. Okay? And now we really have to be working overtime to make sure that we're prepared when that increases by an order of magnitude by 10 times or more, that the computational resources are there, looking at you, RCAC and everything, that the theoretical frameworks are there, right? And the observing network to be able to follow through. It can't be astronomy like we have done in the past, where individual groups target whatever they think is the most interesting thing. To really extract the most science, to really tap into the full potential of Rubin Observatory, there needs to be wide-scale, worldwide, coordinated observations and follow-up. Okay? And if it's not clear, Rubin is a wonderful discovery machine, but as I mentioned, it images a field, it returns that field 3 to 4 nights in a different filter. I don't have multiple filters in the same field in the same night. That's why we need supporting facilities to be able to help fill in the gaps. For instance, a supernova rises over timescales of weeks. That's the timescale for which Rubin will return to the same field with the same filter. In addition to that, we need spectroscopy. That's also to be provided by supporting observatories. In addition, we need multi-wavelength observations that may be ground-based or, in many cases, space-based. Okay? So being able to, on the fly, characterize these supernova explosions, make recommendations, send out alerts to astronomers for us to coordinate and respond to it is a whole new way of doing astronomy.
And I think the really big takeaway is that this was said earlier, I think, in the video, but for supernova and many other fields, in the first year of Rubin, they will discover more supernovae, more asteroids than have been discovered in the entire history of astronomy, is, I think, probably the best way to look at it.
Yeah, this is a very surreal moment. Could we go back to the slides where the idea of the Vera Rubin Observatory came about in 1998, and through a lot of engineering challenges and through a lot of funding things. It's taken a really long time for this telescope to come out, but in this video that Dan made, oh, can I cycle back? How do I, okay. Yeah, you can see the DESI legacy survey and the comparison of the same field through Rubin, and it really is revolutionized in spatial resolution and sensitivity.
Can I mention something else? There's so many details, we won't get to everything. So you have to understand, okay, that's a color image. It's made up of different images used with different filters. You saw some of that in the monochromatic images that they showed. But within 90 seconds of an image like that being taken, okay, they're already comparing it to a template image. So what they do now is they're going to, over the beginning of the survey, will try to, image the full sky so they have a template. Okay? It's the comparison to see if anything changes. So they take a template, and then sometime later, they return to that same image, and they compare it to the template image. And they do it digital subtraction. So anything that changes pops up immediately. So within 90 seconds of that shutter closing and the image being read out, they're comparing it to the previous image. They're making measurements of all the sources, how much it's changed from the previous exposure, and they're sending it out as an alert to the astronomical community. And then that goes to data brokers, which further provide additional information. Are there known galaxies nearby? Are there events that have been in that close proximity? What's the redshift of that galaxy? What's the star formation? All this value added. And then further downstream of that is where something like Refit tries to use all this information to make the forecasting, to see how the transits are going to evolve, and make recommendations to the user community. So again, re-emphasize that this is astronomy unlike we've ever had it before. Typically in the old days, you go to an observatory, you observe your field of sky, you'd come back home and you'd take some time, and weeks later you'd be able to see what has changed. Now within 90 seconds of that exposure being taken, you're distributing it to the world.
Yeah, and I want to also take the time and invite our virtual panelists as well, because I believe they can see the same thing that we are. Do you have any comments on watching that transition back and forth between an old survey and the new one? Just any thoughts that go through your mind seeing it firsthand like that?
Sorry, I can't actually see the slide.
Well, there goes that plan.
I mean, I've seen comparisons before between both Rubin Observatory and this DEC Legacy Survey, as well as with like HST, is crazy. So HST can get just as deep, but Rubin, you go so wide so quick that you can see a lot more things, connect a lot more things with each other with Rubin. And then in comparing it with what DECCAM was able to do, it just kind of blows it out of the water. The amount of depth you can get with the DECCAM survey, that was like a 400-second exposure to get that level where Rubin is 30 seconds-ish.
Yeah, amazing. Professor Peterson, when you look at that galaxy cluster, how does it compare just in your mind? I know you weren't able to see it, but how does it compare to other past survey images that you've seen?
Yeah, it looks great. I mean, in strangely, what I'm most excited about is all the little tiny galaxies behind it, and you really can see just so many galaxies. Some of those galaxies might even be, a substantial fraction of the effective size of the universe away. Um, so yeah, it's just very, very high density of sources in a very short period of time. So it's pretty exciting.
Yeah, if we can put that up one more, well, I don't want to flip back and forth too much, but if you look back between the images, the Rubin and the one, the DESI Legacy Survey, John has it exactly right. You may be distracted by the bright galaxies, but guide your eye to what looks like black in the dark energy camera and what is actually filled with tiny galaxies below it. You're reaching a whole new level. For any of you like me that wear glasses, okay, think about, I remember the first time I got prescription glasses, like, oh my gosh, the world looks like that? And that's what it can be like when you compare what previous imaging surveys have been doing and now what's possible regularly with Rubin.
Yeah, having a ground-based telescope and being able to compare it to images from Hubble and James Webb Space Telescopes, it's really fantastic. It's a marvel that this thing is 8 meters, it's 25 feet in diameter. In fact, I went to the University of Arizona as an undergraduate student, and I was walking home back to my car one day, and I would always pass the football stadium in which underneath is the Richard F. Karras Mirror Lab, and I saw this giant flatbed in the parking lot, and it said LSST on the side, and I was like, oh, that's so strange. Turns out they were shipping it out that day, and since it's 25 feet wide, it's so large, they had to pull over every 30 minutes on the highway to let cars go through because they could only transport it so fast. So it is a really, really incredible piece of machinery. Anyways, we want to turn it over to you all to ask questions for our panelists and for Dan and for Braden and the Johns. We also have the images from the telescope pulled up on the computer that had the slides on it. So if you'd like anybody to go through the images or just have Dan react to them and be excited about them because that's what he does best. Yeah, so I'd like to turn it over to you all if anybody has any questions.
Yep, so just raise your hand and I will run the microphone over to you if anybody wants to be the first. I know that's always daunting.
You have to ask Adina for her reaction because she had a great reaction this morning. Can you comment, Dina, please?
I'm not exactly sure what I was saying, but I think I guess I felt really lucky to be alive, or I guess to be here right now because I feel like it's the perfect place to be, exactly. And I guess it just reinforced me, okay, you're doing the right thing. I'm in the right place. I don't know, just shivers almost. But I do have a question, actually. You mentioned that it might be a while because you're studying supernovae and the time scale and everything before you start using the data. How long do you think it'll be, on an order of weeks or months or years before you or your group starts using this data?
Great question. I don't know off the top of my head. I will say what we're waiting for here, our own science interests, is this stream of alerts to begin. And I don't know if John or John know offhand when that's going to start. There is, as I said, the first phase is when they begin taking the template image of the entire field of, like the entire visible sky, and then the process of comparing the template image. I know in the original engineering work in June, they tested the ability to do the template subtraction, and it was working really well. So it's really just a matter of when they feel comfortable to be able to start sending out that stream of alerts. That's where they on the fly take an image compared to the previous and then send the alert stream to the data brokers. So a part of that is also are the data brokers ready to go from, say, 100,000 alerts from ZTF every night to 10 million alerts from Rubin Observatory. But I anticipate that within the first couple of nights of this stream going live that we're going to start seeing some amazing things. Things that we anticipate, so we have ideas about population scale studies of supernovae that we want to do, but then also the unknown, right? Whenever you turn on a transformational facility like this, there's always the unknown unknowns that just kind of show up. I don't know if, John, can you speak at all? Do you know the time scale for when we may start getting alerts?
I believe that as you were saying, the alert production pipeline is being used and tested right now internally, but I think it could be, I think it's when they think that they're ready. It could be we're now entering what's called the science verification survey, which is going to look very similar to just normal survey operations. But at some point they will say, like, we are ready to go. We're delivering great data products. And so that should happen. That science verification survey should happen should be done by the end of this year. And the survey is supposed to start by the end of the year. And so at the latest then.
Yeah, sorry to interrupt, but yeah, my mind thinks like November, December-ish or something when we may be able to get something, but we'll see.
Right.
Okay, thank you.
And I'm really excited that you're excited, as we all should be.
Going to transition really quickly to a question from Dennis Erickson on YouTube. How often will you have a new template? That's for everybody.
I mean, they continue to build the templates over and over again over the course of the survey. So by the end, every photo that you have will look like the images that we have. Those were, I think, like 600 separate images. So by the end of the survey, you'll have vastly better templates than you do now. But pretty much every image gets verified and added on to the template images.
And it gets a little complicated for supernovae, because what if a supernova is existing in your template image, right? So you can't just blindly choose everything together. One has to be careful, and this is part of the computational challenge about what's the optimal way to develop templates, and maybe you need to curate something for your own science.
Okay, thank you. Anybody else have a question? We have time for a couple more. Oh, all right.
All right, so briefly in the presentation, it actually talked about some of now correct me if I'm wrong, an adaptive optics system that comes with the ground-based telescope. So I was wondering, now with this new unprecedented wide POV of something that would be comparable to, say, the Hubble Space Telescope in a much wider view, I was wondering a little bit of the science behind how the adaptive optics worked. I believe it was called either Oxtel or by its old name Calypso. I was wondering if you guys could explain generally how the science works in those programs for such a wide view telescope, and then perhaps some of the advancements that we made in adaptive optics to allow some of this unprecedented data that we have today.
That's a great question. John, are there views? You're closest.
Yeah, so it doesn't have adaptive optics. Adaptive optics only works for a kind of small field telescope. since LSST Rubin Observatory is the biggest field telescope, it's hard to correct the atmosphere for the entire thing. But it has something called active optics, which is slightly different. That just adjusts the mirror shape as you're going along to try to keep the images in focus and keep them as high resolution as you can get. And it deals with both the sagging of the mirror when you're moving it around as fast as they do, as well as the changes in the thermal environment. It takes a mirror a very long time to kind of come to a constant temperature. It actually never comes to a constant temperature. It's always a little bit off in one part of the mirror than the other. So you correct those things. It just keeps it kind of in focus and keeps the blurring as good as you can, but it doesn't correct the overall blurring due to the atmosphere from the turbulence. That you can only really do on a very small field telescope on the ground.
Yeah.
And
So I know the Simone telescope, it has actuators on what's called M1, the largest part of the mirror, that will push it kind of let it sag or push it up in order to do these corrections. And then you can actually also move the secondary mirror M2 a little bit in order to get everything into focus. How Oxtel is going to work, Oxtel is a 1.3 meter telescope that is just up the hill right on site from the Rubin Observatory. And that has a slitless spectrograph that will be the idea is that you'll have your image with LSST, and then just off to the image, or even a little bit in the image, you'll take an Oxtel image that will give you information about the atmosphere. It's not really going to correct for the turbulence so much as help with color corrections for the data.
Which is amazing. You don't often get a secondary telescope just to focus on monitoring the atmosphere as you use your primary telescope.
Awesome. Thank you very much.
All right, we are nearing the end of our time here, so I want to give our panelists a chance if they have any final thoughts to convey them now. Anything?
Is there a slide about how they can get involved or look at the data themselves?
We did have earlier, there is a link to the Vera Rubin webpage for citizen science. That is something that you can easily find. It doesn't have anything as of yet, but there is something that you can sign up to get more information for if you are looking to get involved. And we can pop that slide up again.
I would just want to plug and recommend that if you're interested in any of the science or anything like this, I think one of the great things that Rubin and LSST have been doing is they have their own funded educational and public outreach program that will go through operations, and they've already created, I want to say, like 10 videos showing and displaying the power of LSST and what it will do, as well as provide many presentations and teaching materials in both English and Spanish.
All right, amazing, thank you. Can we flip back over to the slideshow really quick? While we're doing that, thank you both to our in-person panelists and our virtual panelists. That was an amazing Q&A session, and thank you for joining us throughout this.
Oh, yes. Yeah, this is the slide. So this QR code in the top right corner is the QR code to the Rubin's citizen science page where you can get involved with science. If you want to look at the images from today in beautiful detail, go to rubinobservatory.org, and it's the front page. You'll be able to go through the deep field, the asteroid images, the RR library stars, and the nebulous emission images. Thank you all for coming so much. We are so excited for the future of survey science, and thank you guys for being here for this moment.
Yeah, and specifically thank you to our the Department Head of Physics and Astronomy, Gabor Chathi, the Purdue College of Science for helping us put this on, as well as the Department of Physics and Astronomy itself. Huge shout out to Cheryl Pierce, Nicole Turner, and David Seipel for all your help in getting everything set up today, as well as our video production crew. So thank you very much for joining us, and have a great rest of your Monday.
Yeah, and take some photos in the photo booth. That's right.
Please.